Okay, good morning, ladies and gentlemen. This is Professor David J. De Los Reyes. My topic for this morning will be a random topic, and this falls under the so-called study of integral calculus. So, for those of you who are planning to take up engineering or would like to polish your knowledge of integral calculus, this is for you guys. For those who are taking up the SAT or CAT exams, I don't think this will be coming out in the SAT and CAT exams. So this is just for those who are planning to take up engineering and would like to polish their knowledge of integral calculus. Okay, let's proceed. We are given a problem here. Evaluate the integral of dB all over the square root of small a square minus b square. We are asked to evaluate what will be the result of this one. Okay, let's try to bring out the solution. Actually, this problem here falls under one of the standard equation under the study of integral calculus. And since we are to bring out the solution, after coming out with the solution, we can compare the solution to the standard integration formula, and we shall see if they are really the same. Actually, this was actually the derivation of that standard integration formula. Okay, let's try to bring out the solution. The solution, there is no such thing as trick in the so-called study of integral calculus, because it's better to learn the normal solution. For me, I don't believe in the so-called trick to the solution. Maybe for IQ exams there are some tricks, but for integral calculus there will be no tricks, right? For as long as you know the procedure and how to integrate, I think it's better that we must have to know the standard solution by just, and not by just, I don't believe in the so-called tricks. Okay, let's proceed with the solution. The solution should be by using the so-called trigonometric substitution. Because actually in the solution of this one, we could present two solutions, but I will just be presenting one solution for this morning. And that is by using trigonometric substitution. Because trigonometric substitution solution, actually you will learn so many things because it involves our knowledge of the so-called trigonometry. Okay, let's proceed. Since we are using trigonometric substitution, there must be substitution, right? And the proper trigonometric substitution should be this one here. We will let small b square to be equal to small a square sine square of theta. That will be our trigonometric substitution. There is no trick about this. So the tricks they are saying does not apply here. Okay. Then we try to take the square root of both sides. We raise both sides to the 1/2. Since the highest power of the term on the left is 2, this is 2 and this is 2, and the operation is multiplication, right? So, hallelujah. So actually we can cancel these 2 now, and so with this, and so with this. We can cancel this 2 and 2 as long as the operation on the right is multiplication, right? Because a square times sine square of theta, the operation is multiplication, and we raise that to the 1/2, so actually we can cancel 2 here, we can cancel 2 here, because a is a perfect square, and sine of theta is also a perfect square. So after taking the square root of both sides, b now, because these 2 here cancel also with these 2 here, b now will be equal to e sine of theta. Okay? After this, we will try to take the differential of both sides. Take the differential, it's not derivative, it's just differential. B is a variable, A is constant, theta is variable, okay? So the differential of B will just be simply B, and the differential of the right hand side, we can use the product formula, or there is a standard formula on how to compute for the differential of derivative of a constant in a function. It will just be simply a constant times the differential of that given function. Okay? Because a sine of theta is actually a product, right? Okay? But since this is a constant, there is a standard formula for that one. It will be that constant a times the differential of sine of theta. And the differential of sine of theta is a positive cosine of theta differential theta. Right? So dB will just be simply a cosine of theta differential theta. Okay? Let's go back to the complicated thing, the square root of a square minus b square. We'll go back to this. So the square root of a square minus b square equal to the square root of a square. I'm following this, right? And we'll try to bring out the equivalent of b square from our trigonometric substitution. That is, b square is actually a square sine square of theta. So this is a square sine square of theta. This is minus, right? Okay. There is a common factor a square inside. We can factor it out. And the remaining term will be the product of the quantity 1 minus sine square of theta. Because a square times 1 is a square, and a square times sine square of theta will be a square sine square of theta. So we factor out a square. Okay? And if we try to take the square root of this one, the operation inside is multiplication, considering this quantity here. This is one term, this is another term. So actually, we could take the square root separately. So this will be the square root of e square times the operation inside is multiplication, so we could actually segregate it. So this is times the square root of 1 minus sine square of theta. But the equivalent of sine square of theta is cosine square of theta. Right? The first formula, that is sine square of theta plus cosine square of theta equal to 1. So 1 minus sine square of theta equal to cosine square of theta. We will replace this one by this value here. So this is now the square root of cosine square of theta. This is a perfect square, this is a perfect square, right? And this is under the exponent, the square root. So these two here cancel with this radical sign here. These two here cancel with this radical sign. That's the style here in the USA. But for me, I prefer the exponent thing. But it's the same, alright? And since this is square root and these two here cancels, what remains on the first one will be a. For the second one, it will be cosine of theta. So we needed this equation here in this to go back to the original integral. Okay, we'll go back to the original integral now. We are not yet integrating, we are just making the trigonometric substitution and the so-called simplification before we will proceed with the so-called integration. So going back to the original problem, the integral of dv over the square root of a square minus b square. And this should be equal to, we will now be changing our variable because there is a substitution, right? dB, what is dB? dB is actually the product of a cosine of theta differential theta. This is dB. Okay? And what is the square root of a square minus b square? As per simplification, the equivalent is actually a cosine of theta. So we will be replacing the given denominator by its equivalent from our simplification, which is a cosine of theta. right? Okay, I want to emphasize this one now. This is where many students, what they call this, made a mistake. We can cancel this one now, and so with this, because the operation on the numerator are all multiplication, right? And the denominator is just an alone. So I will try to show that we could cancel it. So a cosine of theta differential theta can be written as the product of quantity a cosine of theta close quantity times differential theta close quantity all over a cosine of theta. The operation is multiplication, right? Multiplication. And we are free to cancel from some of the terms on both the numerator and denominator if the operation is actually multiplication. The operation there is multiplication. And luckily, the denominator is actually a cosine of theta multiplied by 1. Right? Since the operation is multiplication, this is now algebra. This a cosine of theta cancel with this. So what remains will be the integral of a cosine of theta. This will become 1, right? So 1 times differential of theta will be differential theta. And a cosine of theta, since we cancel out, this will become 1. So a 1 times 1 will be, this is actually over 1, or this is just simply the integral of differential of theta. Right? Just take note of the, what I call this cancellation. We can cancel because the operation on the numerator is multiplication. So the integral of the differential of theta will be theta. This is plus c. This is now actually our answer. But we must have to bring out the original variable. The original variable is actually b, small letter b. And where do we get the value of theta? We got it from here. Since b is equal to sine of theta, try to compute for sine of theta. Sine of theta will be equal to, it will be b over a. Okay, so if we try to draw a right triangle, this will be theta. Sine of this angle will be opposite over hypotenuse considering theta. So this should be b, this is a. So the adjacent side will be the square root of a square minus b square. And actually, we can solve for theta now here. The inverse of sine is actually arcsin. So the arcsin of sine of theta will be theta. And the arcsin of b over a will be the arcsin of b over a. Okay, it is this. So the integral of dv over the square root of a square minus b square in terms of the original variable b will be the arcsin of b over a. This is plus c. B here is variable, a is constant, c is just a constant. You notice it, guys? This is one of the standard formulas under the so-called study of integral calculus. That is the integral of dv over the square root of a square minus b square is actually arcsin of b over a. This is plus c. If you try to go back to your table of integration formulas, this is the number one formula under the so-called arcsin function. That is the integral of dv over the square root of a square minus b square is actually arcsin of b over a. This is plus c. You see it, guys? I didn't memorize it. I don't have to memorize this one, but since I know the conventional solution, no tricks, right? I don't believe in tricks. Maybe in the IQ part of the examinations, there are some tricks, but in the integral calculus, there are no tricks. Okay, good morning from Los Angeles. This is Professor David J.